Welcome. Let's have a conversation for this week for foundations. I'm actually going to make only one video and one discussion board this week, and I'm not going to give you any homework. I want you to really focus on these discussion boards because I'm going to give you some things that are really hard to do, and I really want you to tackle them and attempt them, and not being afraid to make some mistakes. So first off, let's just talk about some key definitions. We're going to move into chapter 4 and talk about prime numbers. So what is a factor? If A is divisible by n, if A divides n, then we say that A is a factor of n. So that's kind of the key point, is that whenever I'm dealing with these factors, I have to deal with this. If n is something that only has exactly two distinct prime numbers, two distinct positive factors, meaning it has exactly two different factors that are both positive, not zero. So it doesn't have 3, it doesn't have 5, it has exactly 2, and one of them is 1, and the other one is itself. Those are the only positive factors. Then it is prime. Otherwise, it is not prime. And you can figure out real quickly as to why we actually have a problem here. In fact, your first problem that I want you to figure out is 1 a prime number, yes or no? And why or why not? So again, leverage this definition. Why does 1 not satisfy the definition for prime, or how does it satisfy it? All right. Problem 2, I want you to list the first 10 prime numbers. I know, probably not a big a deal, but in reality, it's to illustrate the idea that the prime numbers are chaotic. They don't really follow a key pattern. First few ones, you can kind of mess around with. Then here's a lemma, and this is where we're going to get fancy. We're going to let n be any natural number greater than 1. So starting at 2. Then n can be expressed as the product of prime numbers. Meaning I can write it as P1 times P2 times P3 times up to Pk. This is a lemma, so we can prove this. How can we prove this? So our question is, this one you actually, and I'll get to this later on, I want you to attempt this one. Hint, you might want to try a proof by contradiction. Suppose it cannot be written as a product of primes. Well, if you write other numbers that are not the product of primes, then that's a problem. And you're gonna have to at least get down to some smallest number that's not the product of primes, and then the question is it prime? So we have all these prime numbers to deal with, and notice they do not necessarily have to be distinct. In other words, we can repeat our prime numbers, like 4 is 2 times 2. That's fine. All right, I want you to attempt this one. All right, let's get to another key definition. This one's going to come up. Let mn be integers such that at least one of them is not 0. Preferably both, but at least one. Then the greatest common divisor, denoted GCD, is the largest positive integer that is a factor of both of them. And if the greatest common divisor is 1, then we call them relatively prime. This is kind of a big deal. So I want you to find the greatest common divisor of 54 and 72 and show your work. We're going to talk about a couple different strategies going forward. Not going to tell you them right now, but this is a great way to learn and think about what have you been learned to find this greatest common divisor of these two, and is there a faster way to actually do that? Now, another kind of important thing is to provide examples of two natural numbers that are relatively prime. I'd prefer if you pick two numbers that are not already prime. Obviously, any two numbers that are both prime are relatively prime, but go ahead and find something else. And then 4.8. Now, this is not one I'm going to make you prove, but I do think this one is kind of interesting. Suppose m and n are relatively prime. That means the greatest common divisor is 1. then there exists some S and T such that NS plus MT is equal to 1. This one is really, really kind of cool. Because it means, so because our greatest common divisor is 1, we can kind of be like, how could we do this? How can we show that this actually has a solution? And there's a lot of different ways to do this, but this becomes the basis of a common number theory strategy to find the greatest common divisor, as well as to actually write them in this form. This, by the way, this form of the equation is called a Diophantine equation, has tons of applications throughout number theory. All right. Oh, I skipped, sorry. So again, you do not need to prove lemma 4.8. Don't have to do that. 4.7, you do. And let's get to 4.9. Let's take the two numbers 2 and 7, which happen to be relatively prime. Can you find the integers s and t such that 2s plus 7t is equal to 1? Hint, they are not distinct, meaning there could be multiple pairs of s and t that satisfy it. I'm curious to see all your different strategies. I know you've all taken different classes and exposure to different strategies potentially to solve this equation. So again, I'd like to see what you guys got. And then two last problems. Sorry. This one, I'm not going to make you prove unless you really want to. It's a bonus question for the week. Assume that P is prime. This one's a kind of a really, really big lemma. If P divides A times B, then either P divides A or P divides B. The proof of this, and I'll just show you real quickly, you have to do a proof by contradiction. In other words, I'm essentially going to have to, my proof, which is a proof by contradiction, would be suppose P divides AB and P does not divide A and P does not divide B. Because the not part, I'm supposing this is not true. And not or means it's cannot true for one and not true for the other one. We then have to show that this is a contradiction. So this thing right here means that there exists an integer k such that pk equals ab. Well, since A and B, we don't know anything else about them. Since this is not true, that P does not divide A and P does not divide B, then we have to know that, but by definition, remember this is a natural number, so this can be written as P1 times P2 times P3 times Pn, where these are a bunch of P's. These are the prime factorization, so to speak, of it. And this gets us in where we get into a problem where now that means that this P either divides one of these P's or and so forth. So this is actually a tricky lemma. It's a little bit, there's some fancy dancy tricks, and I can show anyone who wants me to go through it. But the idea here is this is really, really critical. If P divides, if you have a prime number that divides some product, then that prime number has to divide at least one of those two values. And now I want you to use that then to give an example of ABD, where D divides the product, but D does not divide A and D does not B. Notice I did not say that D has to be prime. So I'm not telling you to try to break this theorem. This is a known theorem. But this is where we're going to apply it. So your homework again, the discussion board, 4.11, 4.9. You're not going to do 4.8. You're going to do 4.7, 4.6, 4.4. I want you to try this one. 4.3, and 4.2. So get at that. Let me know what questions you have. Good luck.